Good morning, everyone. My today's topic is chemistry of D block elements. According to the periodic classification of elements, the elements can be broadly divided into four blocks, namely S, P, D, and F blocks. The division is based upon the type of atomic orbital which receives the last electron in the atom. In the modern periodic table, S block elements are placed on the left hand side and P block elements are placed on the right hand side. The elements which lie in the middle of S and P blocks are called transition elements. These include elements which lie in the middle of S and P block elements. These are the elements of groups 3 to 12 starting from 4th period onwards. In these elements, the outermost shell contains 1 or 2 electrons in their s orbital, but the last electron enters the last but one and d subshell n minus 1d. Therefore, these elements are also called d block elements. The elements of this block have general characteristic properties intermediate between the elements of s block on one hand and p block on the other hand. In other words, d block's elements represent complete change or transition from most electropositive s block elements to least electropositive p block elements and are therefore called transition elements. In addition to d block elements, there are two series of elements placed at the bottom of the periodic table. In these elements, the last electron is added to the third to the outermost energy level. These elements are called inner transition elements because they form transition series with the transition elements of D block. Definition of D block elements: the D block elements may be defined as those elements which have partly filled D subshells in their elementary form or in their commonly occurring oxidation states. This definition covers coinage metals, copper, silver, and gold as transition metals because in their commonly occurring oxidation states they have partly filled d subshells. Because, for example, copper plus 2 has 3d9 configuration, Ag plus 2 has 4d9 configuration, Au plus 3 has 5d8 configuration. Although these all three atoms have completely filled d subshell in their elementary states: copper 3d10, silver 4d10, gold 5d10. However, it may be noted that the above definition does not include elements of group 2b, that is zinc, cadmium, and mercury. These elements do not have partly filled d subshells in their elementary states or in their commonly occurring oxidation states. These elements do not show similarities in properties to the transition elements to any appreciable extent except for the ability to form complexes with ligands such as ammonia, amines, halide ions, etc. However, these may be treated along with transition elements to maintain rational classification of elements. Position of d block elements in the periodic table is shown in the above figure. The transition elements consist of three complete rows of 10 elements and one incomplete row. These rows are called first, second, and third transition series, which involve the filling of 3d, 4d, and 5d orbitals respectively. The fourth transition series is incomplete and involve the filling of 6d orbitals. These series are also called transition series. First transition series: scandium atomic number 21 to zinc atomic number 30. Fourth period, 3d orbitals are gradually filled. Second transition series is from yttrium atomic number 39 to cadmium atomic number 48. It is the fifth period and 4d orbitals are gradually filled. Third transition series is from lanthanum atomic number 57 to hafnium atomic number 72 to mercury Z80. It is in sixth period and 5d orbitals are gradually filled. Fourth transition series: actinium Z is equal to 89 and to Rutherfordium Z is equal to 104 and copernicium Z is equal to 112. Seventh period: 6d orbitals are filled. The end members of the series zinc, cadmium, and mercury have been included, although they do not fit the definition. Position of d block elements in the periodic table. The d block elements or transition elements occupy position in between the s and p block elements in the periodic table. To understand the position of d block elements, let us consider the filling of atomic orbitals with increase in atomic number. The relative variation of the energies of atomic orbitals as a function of atomic number in neutral atoms is shown in figure 2. The main features of above figure are discussed below. General features of electronic configuration of atoms in hydrogen atom. All the subshells of a principal quantum number have same energy. For example, in the fourth principal shell, 4s, 4p, 4d, and 4f subshells have same energies. This is due to the fact that there is only one electron in hydrogen atom and no shielding can take place. In other words, the energy levels in hydrogen atom depend only upon the value of principal quantum number. As we move to multi-electron atoms, it is observed that the various subshells S, P, D, F, etc. in the same principal shell split apart into different energy levels. On moving from one electron system to a multi-electron system, the energies of all the levels drop to lower values. That is, as the atomic number increases, the energy is decreased. The decrease in energy is due to the fact that an electron in a particular orbital is shielded from the nuclear charge by all the other electrons in the atom, and this shielding is insufficient to prevent a steady increase in the effective nuclear charge experienced by that electron with increasing atomic number. In other words, each electron is imperfectly shielded from the nuclear charge by the other electrons. As a result of shielding, the energy of an electron in an atom is given by the relation below, where Z star is the effective nuclear charge. Since the value of Z star increases with increase in atomic number, the energy of electron decreases. It is also clear from figure above that the various subshells do not drop in energy in a regular fashion. This is due to the fact that in different subshells in the same principal shell are not shielded to the same extent, but these SPD and F are shielded differently due to their different shapes. The order of shielding effect of electrons in different orbitals is S have the highest shielding effect and F orbital has the lowest shielding effect. Therefore, because of different extents of shielding, they are attracted to different extents by the nucleus. As a result, they drop in energy to different extents. From figure 2, we observe that the energy levels 1s, 2s, 2p, 3s, and 3p occur in this sequence in all atoms. From the element hydrogen, atomic number 1 to argon, atomic number 18, the above sequence is followed. As the filling of these orbitals take place, the energies of higher unfilled orbitals are affected by the screening power of these 18 electrons. After the filling of 3s and 3p subshells, we expect that the next electron of potassium, atomic number 19, should enter the 3d subshell. However, potassium belongs to S block and the next electron after argon enters the S4s subshell and not 3d subshell. This anomalous behavior can be explained on the basis of penetration power of different subshells to the nucleus. The different subshells have different penetration powers, and the orbital which penetrates more to the nucleus will be less shielded from the electrons and therefore feels more nuclear charge. As a result, it will be more strongly attracted by the nucleus and will have lower energy. The extent of penetration of different subshells in a given principal shell is given below. The penetration power of 4s orbital is very large, so that it is attracted more by the nucleus than even 3d orbital. As a result, the energy of 4s subshell is lower than that of 3d subshell. This can also be easily understood from the radial probability distribution curves of 3d and 4s orbitals as shown in figure below. As evident, the radius of maximum probability for 4s electron is much farther from the nucleus than that of a 3d electron. However, in the contrast to 3d electron curve, there are three small peaks closer to the nucleus which show that 4s electron penetrates the inner core of 1s2, 2s2, 2p6, 3s2, 3p6 known as argon core. The penetration effect is more than to compensate the larger distance of main peak. As a result, 4s electron is held more tightly to the nucleus than 3d electron and hence 4s orbital has lower energy than 3d orbital. Therefore, in potassium, Z is equal to 19 and calcium, atomic number 20, the outermost electron enters the 4s orbital. As these two electrons are added, the nuclear charge is also increased by 2 units. At atomic number 21, the 3d orbitals penetrate the electron density in the 4s orbitals considerably, so that the effective nuclear charge for 3d orbitals increases, and as a result, they drop to lower energy than the 4p orbitals to about the same level of 4s orbital. Therefore, the next electron in scandium, atomic number 21, enters the 3d subshell. The electronic configuration of scandium is 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2. The electron in 3D orbital screens the 4p level more effectively than it screens the remaining 3D orbitals. So the energy of 3D subshell remains the lowest and the next electrons from titanium enters the 3D subshell until 3D subshell gets completely filled. Thus, zinc with atomic number 30 has the electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. These elements from scandium to zinc involving the filling of 3D subshell constitute first transition series. After the completion of 3D subshell, the 4p subshell becomes lowest in energy, and therefore the next six elements from gallium to krypton, atomic number 36, involve the filling of 4p subshell. The electronic configuration of krypton is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6. After krypton, the filling of electrons in different subshells follows the same pattern as we had observed at argon. As in the case of 3d subshells, the 4d subshells are higher than 5s subshell because of shielding effects. Therefore, the next two elements, rubidium and strontium, involve the filling of 5s subshell. After filling 5s subshell, 4d subshell is lower in energy than 5p and is therefore filled first. The next incoming electron in yttrium, atomic number 39, is added to 4d orbital, which has the configuration krypton 4d15s2. The addition of electrons continues till second transition series is completed at cadmium, having electronic configuration krypton 4d105s2. The elements from yttrium to cadmium constitute second transition series. The next six electrons enter the 5p subshell, and therefore xenon atomic number 54 has a configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 4d10, 5s2, 5p6. After xenon, the same sequence of energy levels is repeated again. The 6s orbitals are filled after 5p, so that next two electrons are added to give 6s, giving an alkali and alkaline earth metal cesium and barium respectively. However, the 6s subshell scarcely shields the 4f orbitals, so that they abruptly feel an increase in effective nuclear charge and therefore drop in energy. At the same time, the energy of 5d levels also decrease abruptly, so that the energies of 4d, 5d, and 4f orbitals become almost equal. The next entering electron in the element lanthanum enters a 5d orbital because the next elements from cerium to ytterbium involve the filling of 4f orbitals. Therefore, the configuration of cerium is xenon 6s2 4f2, and that of ytterbium is xenon 6s2 4f14. The elements from cerium to ytterbium, which involve the filling of 4f orbitals, are known as lanthanides and constitute f block. After ytterbium, the next electron enters the 5d subshell, and therefore the elements from lutetium to mercury involve the filling of 5d orbitals. These constitute third transition series. Following mercury, the next six elements involve the filling of 6p orbitals until the next noble gas radon. The electronic configuration of radon is xenon 4f14, 5d10, 6s2, 6p6. The next two elements after radon involve the filling of 7s orbitals. As in case of 4f and 5d orbitals, the energies of 5s and 6d are almost equal and both are stable than 7p orbital because of penetration power. Therefore, the sequence of 5f, 6d, and 7p is followed. The sequence of energy levels is given in Figure 4a, and as an aid to memory, a method for remembering the sequence is given in 4b. Electronic configurations of the atoms and ions of transition series. The d block elements have partially filled d orbitals in their neutral atoms, and the general electronic configuration for the atoms of d block elements may be written as n-1 d1 to 10 ns1 to 2, where n-1 stands for penultimate shell, and the d block element or the d orbital may have 1 to 10 electrons, and the s block orbital of outermost shell may have 1 or 2 electrons. First transition series. The first transition series consists of elements from scandium atomic number 21 to zinc atomic number 30. In scandium, the 3D orbitals start filling up and its electronic configuration is argon 3d14s2. As we move from scandium onwards, 3D orbitals gets filled up more and more till the last element, zinc, in which the 3D orbitals are completely filled, that is argon 3d10 4s2. The electronic configurations of the outer shells of these elements are given in table below. The elements of first transition series are scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. It may be noted that the configuration of chromium and copper are anomalous. This is due to the reason that the half-filled and completely filled electronic configuration have extra stability associated with them. Moreover, the energy difference between 3d and 4s orbitals is not large enough to prevent the electron entering the 3d orbitals. Thus, to acquire increased stability, one of the 4s electrons goes to the nearby 3d orbitals so that 3d orbitals become half filled in case of chromium and completely filled in case of copper respectively. Therefore, the electronic configuration of chromium is argon 3d54s1 rather than argon 3d44s2, while that of copper is argon 3d10 4s1 instead of argon 3d9 4s2. Second transition series. The second transition series consists of elements from yttrium to cadmium. This series involves the filling of 4d orbitals as given in table 2. The elements of second transition series are yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, and cadmium. In this series, there are more irregularities in comparison to those in the first transition series. The anomalous configurations of molybdenum and silver are due to the reason that half filled and completely filled electronic configuration, that is D5 and D10, have extra stability associated with them. Thus, to acquire increased stability, one of the 5s electron goes to nearby 4d orbital so that 4d orbitals become half filled in case of molybdenum and completely filled in case of silver respectively. Thus, the electronic configuration of molybdenum is 4d5 5s1 rather than 4d4 5s2, while that of silver is 4d10 5s1 rather than 4d9 5s2. However, the other anomalous configurations cannot be easily explained. It has been observed that factors like nuclear electron and electron-electron forces play significant roles in determining the electronic configuration of these atoms. It may be noted that the element technetium is a synthetic transition metal which has made artificially. This was named so because the word technetium means artificial. Third transition series. This series consists of elements lanthanum atomic number 57 and from hafnium atomic number 72 to mercury atomic number 80. In between lanthanum and hafnium, there are 14 elements called lanthanides which involve the filling of 4f orbitals and do not belong to this series. The next 10 elements from hafnium to mercury belong to third transition series. The elements of this series involve the gradual filling of 5d orbitals. The elements of third transition series are lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury. Like second transition series, there are many anomalous configurations. Fourth transition series, it involves the filling of 6d subshell starting from actinium atomic number 89 and which has the configuration 6d17s2. The next rutherfordium atomic number 104 has the electronic configuration 5f14 6d2 7s2. The elements of fourth transition series are actinium, rutherfordium, hanium, seaborgium, borium, hassium, meitnerium, darmstadium, Rontgium, copernicium. Electronic configurations of ions. Ions of transition elements are formed by the loss of electrons from the atoms. The electronic forces, interelectronic forces, and variation in total nuclear charge plays an important role in determining the electronic configuration of ions. For example, 4s orbital is filled before 3d orbitals, and therefore we cannot say that 4s orbitals are always more stable than 3d orbitals. If this were true, then all the elements of the first transition series should ionize by the loss of 3d electrons, but this is not so. In fact, they ionize by the loss of 4s electrons first. The reason for this behavior is that after the electrons have entered 3d subshell, the energy of 3d subshell becomes lower than that of 4s subshell. As a result, 3d orbitals becomes more stable than 4s orbitals. Thus, in the first transition series, it is the 4s orbital which has higher energy, which loses electrons first as compared to 3d orbitals. Therefore, we cannot generalize that 4s orbitals are always more stable than 3d orbitals because they were filled first. The actual behavior is explained on the basis of net effect of following forces: nucleus electron attractions, electron electron repulsions, shielding of one electron by others, exchange forces. Thus, in the first transition series, 4s electrons are removed first, then the 3d electrons. For example, titanium atomic number 22 has the electronic configuration argon 3d2 4s2. Therefore, the electronic configuration of titanium and Ti plus 2 and Ti plus 3 will be as Ti plus 2 argon 3d2, Ti plus 3 argon 3d1. The electronic configuration of some atoms and ions are given in the table below. Note: it should be remembered that the electronic configurations of the atoms in the second and third rows do not always follow the pattern of the first row. For example, in the series of elements belonging to the group 10, nickel and palladium and platinum, the electronic configurations of the atoms of these elements are different. However, the electronic configurations of ions of same charges are similar. Thank you.